we discussed about nucleus, its properties, then nuclear force and its properties. Today let us discuss about binding energy and mass energy relation.
Dear students, let's start our topic stability of the nucleus. Like atomic energy level diagram, nucleus also have energy levels. We know that nucleons are fermions, that is neutrons and protons are fermions. So they should obey Pauli's exclusion principle. So each nuclear energy level can occupy only two protons or two neutrons of opposite spin. So energy level are filled in such a way that the configuration have minimum energy and maximum stability. The particle occupy the energy levels in order to attain minimum energy and maximum stability. Let us examine the energy level diagram of carbon and boron isotopes. Here boron 510 means 5 protons and 5 neutrons. Here mass number is 10 means 5 is atomic number, that is number of proton present is 5. Number of neutrons, in order to get number of neutrons, A, that is 10 minus atomic number 5 will give you 5. 10 minus 5 will give you 5. So 5 number of neutrons also. So 1, 2, 3, 4, 5. 5 neutrons and 5 protons. So 1, 2, 3, 4, 5. 5 protons. So this is the energy level diagram of boron. We know that this is completely filled and this is completely filled, and here it is half filled. In the case of boron also, boron 511, here number of neutron is 6. 11 minus 5, 6 neutron present. So this is 1, 2, 3, 4, 5, 6. This is completely filled and this is half filled. So boron 511 also is stable nucleus. Let us examine about the boron 512 nucleus. So here is an unfilled energy level, also unfilled energy level. So due to this configuration, this is an unstable one. Carbon 612 is stable because all the energy level are stable. Because carbon has 6 protons and 6 neutrons. Then what about carbon 613? It is an isotope of carbon. What is an isotope? A nucleus or atoms having same atomic number and different mass number is known as an isotope. So they have same atomic number, that is same number of protons present, but number of proton present will be different. So here it have 7 neutrons and this carbon 612 have 6 neutrons. So they are isotope. So this is also a stable isotope because this, up to this completely filled and this is an half filled state. So we can explain the stability of the nucleus using the energy level diagram. Okay, let us discuss about the stability of the nucleus. So nucleus may be of 3 types, that is even nucleus, even odd nucleus, or odd even nucleus, or odd nucleus. Even nucleus is nothing but it have an even number of protons and even number of neutrons. Odd nucleus have odd number of protons and odd number of neutrons. Even nuclei are more stable than odd even or even odd nuclei. That is more stable than odd nuclei. So odd nucleus is the least stable nucleus. But some odd nucleus are stable. Some lighter odd nucleus are stable. For example, H12, Le36, B510, N714, T873, 180 are stable odd nucleus. Here in the case of H12, 1 protons and 1 neutron. So this is an odd nuclei. Lithium 3 protons and 3 neutrons. So this is again an odd stable nuclei. Boron 5 proton and 5 neutron are again stable odd nuclei. nitrogen 714, 7 proton plus 7 neutron is again an ordered nuclei. So tantalum 73, 180, 73 proton and 107 neutron is again stable. So stable ordered nucleus are very less in number. Most of the stable nuclei are even nucleus. 60% of the stable nuclei are even nuclei. There are lot of exceptions are there. All the even nuclei are not stable, and all odd even or even odd nuclei are not stable, and all odd nuclei are not unstable. There are lot of exceptions in the case of nuclei. The heaviest stable nucleus is bismuth 83-209. Heavy nucleus with atomic number 8 greater than 83 and mass number greater than 209 are unstable. So they emit alpha, beta and gamma particle in order to attain stability, and due to this spontaneous emission, they transform into lighter nucleus. Next important topic is binding energy. It is a missing energy that keep the nucleus together. Binding energy is the minimum energy required to disassemble the nucleus into its constituents particle. That is minimum energy required to disassemble a nucleus into protons and neutrons. Or it is the energy that is emitted when a nucleus is formed from its constituent particles. That is, when we add the total mass of protons and neutrons inside the nucleus, then you will get a mass, the total mass of the protons and neutrons minus the mass of the nucleus. There is a slight difference between these two, and that mass difference is known as the mass defect. The mass of an atomic nucleus is less than the sum of individual masses of the free constituents, protons and neutrons. So the corresponding difference in mass is known as the mass defect, and the energy corresponding to it is known as the binding energy. So the energy calculation formula is E is equal to mc square. So m is mass defect and c is the velocity of the light. It is not 2, it is square, c square. So E is equal to mc square will give you the energy corresponding to the missing mass. So now we are going to calculate what is binding energy and what is the energy equivalent to 1U. So we know that the binding energy is equal to delta m into c square, where delta m is the mass defect, c is the velocity of the light. So suppose this is the nucleus. When we give binding energy into this nucleus, it will split into nucleons. That is, it will split into protons and neutrons. So the minimum energy required for the splitting is known as the binding energy. We already discussed that 1 AMU, that is 1 U, atomic mass unit, is equal to 1.67 into 10 raised to minus 27 kilogram. Now we are going to calculate what is the energy equivalent to 1 U. So E is equal to mc square. E is equal to 1.67 into 10 raised to minus 27 into 3 into 10 raised to 8. This is c, velocity of light, the whole square. That much joule of energy is given, is equal to 1.67 into 9 into 10 raised to minus 11, this much joule of energy. So in order to convert joule into MeV, we divide this by 1.6 into 10 raised to minus 13. Why this 10 raised to minus 13 means? The charge of the electron is 1.6 into 10 raised to minus 90. Then you will get energy in electron volt. So in order to convert the electron volt into MeV, MeV is 10 raised to 6. So 10 raised to 6 into 10 raised to minus 19, you will get 10 raised to minus 13. So in order to convert energy in joule into MeV, we have to divide it with 1.6 into 10 raised to minus 13. So you will get this as, that is approximately equal to 931.5 MeV. So this is the energy corresponding to 1 U. And we can express its mass in MeV. So we know that E is equal to mc square. So m is given by E by c square. E is 931.5 MeV. So 1 U is equal to 931.5 MeV by c square. Don't forget the c square, because here in the left hand side this is in mass. So right hand side RHS should be the dimension of mass, should have the dimension of mass. So 1 U is equal to 931.5 MeV by c square. Next, let us calculate the rest mass of electron, the mass of the electron in MeV. So for this, we know that the rest mass of the electron is 9.1 into 10 raised to minus 31. This is in the order of 31, because electrons are very light particles. Its mass is very small. So this is equal to 9.1 into 10 raised to minus 31 kilogram. So we can convert this into energy. So that is equal to 9.1 into 10 raised to minus 31 kilogram into 3 into 10 raised to 8 meter per second whole square. So you will get m is equal to 8.19 into 10 raised to minus 14 joule. In order to convert this into electron volt, this is energy in joule. So in order to convert this into electron volt, we have to divide it by Q, or electric charge E. So 8.19 into 10 raised to minus 14 into 1.6 into 10 raised to minus 19 inverse means divided by 1.6 into 10 raised to minus 19, that much electron volt. So in order to convert this electron volt into MeV, you will get, you have to multiply it with 10 raised to 3, or we can divide it by 1.6 into 10 raised to minus 16. Okay, so that we did in the previous slide. So you will get 5.1188 into 10 raised to 3 electron volt, that is equal to 0.511 MeV, because MeV is 10 raised to 6 electron volt. So you will get 0.511 MeV. So this table, mass in terms of energy table, will give you the mass of different particles, that is proton, neutron and electron in terms of kilogram, U and in MeV by c square. So atomic AMU, we know that 1.660 into 10 raised to minus 27, that is exactly 1 U, that is equal to energy corresponding to that mass is equal to 931.5 MeV, and this mass can be expressed as 931.5 MeV by c square. And neutron mass is this, and this is corresponding to 1.008664 U. So that is equal to 939.57 MeV by c square. So this is the proton mass, and this is the corresponding mass in U, and this is mass in MeV by c square. So this is the electron mass is equal to 9.109390 into 10 raised to minus 31 kilogram. So when you compare the mass of proton and mass of neutron, this is in the order of, all these are in the order of 10 raised to minus 27, but this is in the order of 10 raised to minus 31. So electrons are very lighter particle when compared to protons and neutrons. So mass equivalent of electron is equal to 0.511 MeV by c square. So this is around, in the proton neutron masses are around or approximately equal to 1000 MeV by c square. They are in the order of 1000 MeV by c square, but we know that the electron mass in the order of 0.5 MeV by c square. Let us examine a problem related to this topic. Find the mass defect of copper 63 nucleus. If actual mass of the copper is 63 actual mass of the copper 63 nucleus is 62.91367 AMU. Find the composition of the copper 63 nucleus and determine the combined mass of its components. The copper have 29 protons. So the number of neutron is 63 minus 29, that is given by 34 neutrons. So the copper contain 29 protons and 34 neutrons. So the composition of this is the composition of the copper. So let us find out what is the combined mass of the particles. So mass of the proton is 1.00728 and mass of neutron is 1.00869. So the combined mass is 29 protons into mass of the proton in AMU plus 34 neutron into mass of neutron in AMU. So when we do this calculation, 29 into 1.00728 plus 34 into 1.00867, you will get this as 63.50590 AMU. So the mass defect. What is mass defect? This is the total mass of protons and neutrons minus the actual mass of the nucleus. So that is given 62.91367. So the difference in mass of this and this, that is 63.50590 minus 62.91367. Then you will get it as mass defect as 0.59223 AMU. So we know that 1 AMU is equal to 931.5 MeV by C square. So the binding energy is equal to 0.59223 AMU into C square. So you will get this as 0.59223 into 931.5 MeV. So this is the energy corresponding to AMU 931.5. So you will get this as this much energy. Then let us find what is binding energy per nucleon. Is nothing but the binding energy divided by number of nucleon present, that is nothing but the mass number of the atom. So binding energy per nucleon is given by, or binding energy per number of particle present inside the nucleus. So that is binding energy per nucleon. So that is equal to 0.59223 into 931 point divided by 63. Total number of nucleon present inside the nucleus is 63. So that value is 8.758 MeV per nucleon. So this is known as the binding energy per nucleon.
Okay, dear students. So which nucleus will be more stable? Yes, even nucleus is more stable than even odd nucleus. It is again stable than odd nucleus. So what is the binding energy? Binding energy is nothing but it is the minimum energy required to split a nucleus to its constituent particle. Again, how can we calculate the energy equivalent to mass? We can calculate energy equivalent to mass by Einstein's famous formula E is equal to mc square. Okay, thank you.